thank you for everyone to join this important session on predicting the unpredictable, how data and models can empower early warning, which is part of our global webinar series on advancing early warning for all. This happens to be our webinar 2, which we are going to bring together global experts from leading meteorological and climate institutions around the world, how we can really unpack the predictive power of early warning with novel data sets, Earth observation, and modeling tools. In terms of how we anticipate, the disaster is going to strike, because without knowing that, it will be quite challenging when it comes to early action across the actors, that they are humanitarian actors, respond agencies. They can work together, whether it's a development partner, the local government, and the science is very, very critical. The previous session, we focused on the foundation behind the early warning for all. This segment is, as I said, it's focused more on the how science can inform better action plan when it comes to early warning system. So I'm really thankful to our distinguished speaker and also the panelists for sharing their insights throughout the session for 1 hour or so. Let me introduce Dr. Raghavendra Ashrit. He is a senior scientist at the National Center for Medium Range Weather Forecasting Center in Noida, India, which is under the Ministry of Earth System, Government of India. Prior to that, he also worked with the Indian Institute of Tropical Meteorology and the University of Pune. He specializes in ensemble prediction, high impact weather events, and the spatial verification methods. His research focus on enhancing weather forecast accuracy for India, focusing on monsoon, cyclones, and climate change impact. So over to you, Dr. Raghavendra. You have got 15 minutes to brief our audience. Thank you so much again.
Thank you, Giriraj. It's a pleasure to be part of the webinar series. Yeah, today's topic is of immense importance for every community in the world. So I'll try and touch upon the extreme rainfall events and early warnings with a bit of focus on the Indian region, but I'm sure it's equally relevant for other parts of the world. You can go to the next one. Everyone may recall the Mumbai deluge of 2005. It was about 994 millimeters of rainfall in 24 hours. That actually amounted to a significant portion of seasonal total rainfall in one day. So typically, the pictures tell the whole story, and this heavy rainfall during the monsoon season is nothing new to the city of Mumbai, but this was something extraordinary. It was out of the blue, and generally it's like sporadic events out of the blue, as we can say, something unusual. It's quick to feel, but once it is done, like, the impact is there to be seen. This kind of events in other parts of country and other parts of the world also, it's a challenge for numerical models. Even the numerical models which have generally good skill in predicting large scale patterns, large scale low pressure systems, disturbances producing rainfall, synoptic features. Models are generally good in predicting, and generally operational agencies make use of NWP forecasts to issue warnings. But some of these kinds of events throw up once in a while, they create havoc and leave the forecasters perplexed. And yeah, it gives. This typically happens when the models fail to precisely predict the intensity, because models generally tend to either overestimate or underestimate the intensity of rainfall, location of rainfall, sudden growth and development, and things like that. When the models fail, then that becomes a big challenge for the forecasters to make use of NWP systems and issue the warnings. And that is where like this kind of extreme events, can go to the next one. It becomes a big challenge for the forecaster. Similarly, we had event over the city of Chennai also once in 2015, and similarly in 2023 we had a similar kind of event, as the pictures can show. Like, entire airport terminal was inundated, and there was, like, completely, like you can see in the images where can tell the story themselves. Can go to the next one. So overall, in my talk with this brief snapshot of as the background, I wish to cover a little bit on what are the extreme events and how do we understand them, and also give a perspective from the climate change scenario, a little bit like what the IPCC AR6 has to say about the historically what has been happening and how it can happen in future, and also how the WMO has um, compiled various information and best practices and methods to handle extreme weather related events, and I'll briefly touch upon that, and with bit more focus on the extreme events over India and at NCMRWF, how we are trying to try different approaches to help the forecasters to issue the heavy rainfall warnings. Heavy rainfalls are quite common in every season, but something extreme, something beyond the heavy rains and very heavy rains, extremes are the ones challenges, and we are trying to build different tools to help the forecasters to predict the extreme kind of rainfall events. And then I'll briefly touch upon the kinds of challenges that we face, and how is there possibility of AIML kind of new approaches that can help us in the coming days. This is the brief outline of my presentation. Yeah, what is an extreme? Like going by the definition, like extreme events are the events at the tail of the statistical distribution. This is a very academic kind of definition, we can say. But as we can see on the right top, I have indicated like extremes can be understood in terms of their highest values or lowest values, either in terms of the magnitudes or how frequently they occur, how rarely they occur, something in terms of the frequency, something which has not occurred in the last 100 years in those terms. Or sometimes we can also understand extreme in terms of the impact they leave behind. That could be, we can understand in terms of the severity of the event. So there could be any number of methods that could be used to establish what represents an extreme. It's especially extreme one-day event. It's highly variable in the climates, similar to the climates of as highly variable as India, whether it's a one-day extreme rainfall, one-day extreme temperature. So this was like some very early studies in the 90s. Observations were made with long historical records. Like it's typically not a very easy way to define extreme event. But what can for sure we can say is they are very severe. They come with a lot of strong impacts. Extreme events bring severe impacts on life and property, socioeconomic, and things like that. And they are also very rare, unexpected, sudden. They occur when it's like unprepared and things like that. So it becomes difficult to manage and cope with such rare events. And also they need forecasts. Like we already know that NWP models everywhere in the world are like becoming more and more sophisticated. They use high resolution modeling facilities, supercomputers, or sophisticated data simulation systems. Everything is being used, and there is a continuous improvement in the last 25, 30 years. We see improved skill in forecasting and things like that. And that also true is for because of the improved resolution and all, models are gaining, like they're able to capture high resolution processes and all. So there is expectation that we should be able to do much better job in terms of predicting extreme events, and because they cause serious impact. And that's the thing. In addition to that, we also have a changing weather and climate events under the 20th century. Extreme rain trends have there is a trend, like weather and climate is all impacted due to global warming and things like that, and that poses an extra challenge, like in terms of we can see already that climate change has resulted in projections in future indicate increase in the frequency and in intensity of extreme events. This is all recorded in the IPCC reports. We can go to the next. So based on all the considerations, Of course, every region, depending on the climatology, we can have a definition, or depending on the impact, vulnerability, and different factors. WMO has guidelines for monitoring extreme weather and climate events, and it typically gives some guidelines there, like really useful for taking up, preparing the monitoring strategies and also forecasting strategies. I have just underscored here for the benefit. We can read it like a precipitation is considered in event is considered to be an extreme value if it exceeds a certain threshold that has certain associated impact. So we can have we have the practice in India. We have the practice of heavy rainfall thresholds and extremely heavy rainfall thresholds, very heavy rainfall thresholds. Like the different classification is used in practice, and similarly, the events can also be considered based on the rarity. So there, the option could be like we can, based on the climatology, we can choose the 90th percentile, 95th percentile, or the 99th percentile of precipitation event. So this makes it very not so user friendly, but for the forecaster to identify and isolate in terms of the historical data, that makes it more robust. And yeah, that is one definition. Go to the next one. So it has been outlined in the IPCC AR6, like all over the world. Like the three panels on the left show the trends. In the top panel shows for hot extremes, middle panel shows for heavy rainfall, and the bottom for agricultural and ecological droughts. We can focus for the middle panel, which clearly indicates different parts, large parts of Asia. Each of those hexagons show different regions like South Asia, East Central Asia, and things like that. So everywhere, like the precipitation, heavy precipitation is on an increasing trend. That is something very significant, and it's also based on very systematic analysis of the historical records and assessed and thoroughly reviewed, and this is available. And it is also noted that the climate change is intensifying the water cycle, and that has been happening, and this brings more intense rainfall and associated flooding, as well as more intense drought in many areas. And the climate change is affecting rainfall patterns, not just the intensity, but also their distribution. In higher latitudes, precipitation is likely to increase, while it is projected to decrease over large parts of subtropics. So the changes in monsoon precipitation are expected, which are which they again there is uh, it is not uniform across the region. You can go to the next slide. Yeah, that's with that as a focus. Like WMO also has outlined various finer points. I would like to just, instead of reading the whole thing, I would just like to draw your attention to the fact that the extreme daily precipitation events are projected to increase by about 7% for every degree Celsius rise in the global temperatures. This is very significant. We have tried to limit it to 1.5 degrees, and there is a very good reason why we should be doing it, because it has been quantified that a 7% increase in extreme precipitation can mean increased frequency of inundation, flooding in large parts, and probably in areas which are not traditionally flood prone. That can also happen because there is variations in terms of distribution of extreme precipitation and things like that. Of course, associated impacts can also occur via tropical cyclones, because they also, under the influence of climate change, they also have more intensification, longer spells, increased rainfall duration, and things like that, change in tracks. So there are a lot of changes and possibilities that can lead to making the disaster and the preparedness more and more challenging. So yeah, the compounding effects of uh, disasters can also lead to, yeah, the challenges in future. Go to the next one.
Dr. Raghavendra, you have got 5 minutes to wrap up.
Yeah, I think I'll not dwell too much into it. This is just the trend typically over Indian region. The bottom panels we can see is a sharp increasing trend in terms of the frequency of extreme events and also the widespread extreme event that has been very well documented over India. Go to the next one. Yeah, this is typically the Mumbai case. What we see is what makes it difficult is these extreme events become like the rogue events, and they actually tamper with the statistics, and it becomes difficult to. They always remain as outliers, and the forecasters has challenge in dealing with this kind of events. Go to the next one. Just you can go to the next one. I'll just try to highlight what are the new kinds of. Yeah, this is one example where we have tried to show how ensemble forecasts can be used to isolate and indicate for the forecaster just by computing the in terms of expressing your forecast probabilities, whether they exceed the climatological 1 standard deviation, 2 standard deviation, or 3 standard deviation. That kind of an experiment we did for the Kerala heavy rainfall event for the west coast of India. Go to the next one. Some of the operational products that we are using is shown here for heavy rainfall over Chennai region. You can go to the next one. The probabilistic approach, we have demonstrated that it actually allows us to isolate and pinpoint where the likelihood of heavy rainfall event occurs. This was one particular case of 4th December 2023. So typically December 4th, it's the northeast monsoon, and this time it's expected, but associated with a low pressure system and all, you end up having like very unusually heavy rainfall events. Go to the next one. Yeah, this is actually, I was talking about how we can express our forecast in terms of climatological 90th percentile and 99th percentile, things like that, which will actually allow us to isolate and see the signal. That is one. These are actually operational products. Go to the next one. We further devised tools to actually see it 3 days ahead, 4 days ahead, so that based on the neighborhood, even not just one location, but the neighborhood considerations are also taken into account to actually see what are the high probability chances of heavy precipitation and different amounts that is also constructed. These are the different kinds of tools that we are using operationally. Go to the next one. This is something which ECMWF has developed, Extreme Forecast Index. Of course, I'll not go into the details. I have shared the slides. This is again, the idea is to express your forecast in terms of the climatological extremes. Go to the next one. So similar products we have to isolate for the temperature as well as rainfall, wherein this actually gives a types of bias correction for the forecast, and the actual biases in the forecast are removed, and heavy rainfall is also is the focus. Heavy rainfall and precipitation, we have produced this kind of extreme forecast index. Go to the next one. Just I'll touch upon the challenges and yeah. Similarly, I think we can skip next 3 slides. Based on extreme value analysis, we have devised some tools so as to isolate similar kind of event. Go to the next one. Yeah, you can skip this. Yeah, just the challenges I have tried to outline here. See, observations itself throws a big challenge because many isolated areas and all, no, we don't get data and all. Many times it does happen that especially in the hilly regions of northwest India and all, when there is a cloudburst and things like that, it's only through reportings that we come to know that such a devastation has happened. Some remote places, when remote places experience this kind of extreme events, it becomes very difficult to even confirm based on satellite images or some proxy data, that because data itself is a big challenge. Of course, now more and more increased use of satellite and radar technologies should help us to overcome this kind of shortcomings. Next is the modeling systems. Modelings also have this kind of biases. Next, in future, like probably AI/ML can help. Still, there is this thing like AI. There is a lot of hype about the use of AI/ML and things like that. But yeah, I'm still skeptic about it, like whether AIML can help us predict the unseen data, like something which is not in the historical records, because AIML, they require long period records for training and things like that. But what happens if there is an extreme event which was not seen before? So how can AIML still predict that? That's the kind of it's a challenge. Like precision of location and timing is also still a challenge that we have to see. Just go to the next one. I think I'm almost pretty much done. I'm looking forward with a lot of hope that AI/ML could be useful, may not be effect as I was saying about the unseen data, and need methods which can predict from the unseen data. Probably they are there because some of the uh, pattern recognition and face matching algorithms claim to have such techniques possible. And climate change simulations can be used, long period records when they are not available. Climate change simulations, the historical climate change simulations could be useful for AI/ML. And extreme value analysis and return period analysis. See, these are some of the techniques that have not been fully exploited. They are historically used only for monitoring and characterization. As a forecasting tool, they have not been used. I see full potential, a lot of potential in using some of these techniques along with AI/ML in future. I'm sorry if I have exceeded my time, but thank you. And I'd be happy to collaborate with everybody and hear to the ideas, questions, and comments from others. Thank you.
Thank
All
you,
right. All right.
Raghavendra. Over to Dr. Fulco to moderate the session.
Okay, thanks a lot. My name is Fulco Ludwig. I'm the Director of Water Data Science at IWMI, and I'll moderate the coming up session. First of all, I'd like to ask the public: is there any questions for Dr. Ashrit? So you can raise your hand if you have a question. You can also put them in the Q&A section, which you can find on the bottom. Any questions for Dr. Ashrit? Is there any hands raised? Maybe no. If not from the public, then I have a question. So how do you deal in India with if you look at early warning systems? One of it's always bad to miss an extreme event, but it's also not good if you give a warning and not much happens, which might lead to warning fatigue. So how are you guys dealing with that?
Yeah, that's a very challenging question. And the operational agency in India, the India Met Department, they, the forecasters, we closely work with the forecasters. We closely follow the models and its models' behavior for any particular region, any particular season. And we know the skill of our model over certain regions and certain season, where it is good, when it is more reliable, and things like that. Based on that, on the that we use as a background knowledge to trust a particular forecast and make a judgment. And we also cross-check with other modeling centers like ECMWF, UK Met Office, the consensus forecast. And we also keep tracking which forecast is consistent, which forecast is jumpy or frequently inconsistent, and things like that. Some of these considerations are taken before the forecasters issue the forecast. Ultimately, the forecasters' warning are based on not just one modeling framework. They also use their own experience and the ground truth, what is happening over the region and things like that. And accordingly, they issue impact-based forecasts. They have color-coded categories of forecasting so that they will have room for correction, for warning, and also de-warning. So 3 days before they issue a yellow warning or things like that. When they are more and more sure, they issue an orange warning, yellow, orange, and red, like that. They take all precautions to not do over warning as well as under warning and things like that. They take ensure to do that. Yeah, they operational agencies do a good job in handling.
Okay, thank you. I think there's one question in the chat, and that person is asking: are we saying that there are no machine learning or AI models to predict the unseen forecast?
Yeah, as of now, it appears like that, but I may be wrong because in other fields, other areas, the way AI/ML techniques have been used to overcome this kind of challenges. It says, but in the field of weather and climate, and especially in terms for extreme weather warnings and things like that, I'm still yet to see a credible example. And moreover, it becomes a challenge. But there could be one particular event somebody may be able to predict, but yeah, like consistently, if it could be shown that in the all the 50 events of the past 50 years we could predict, and they were not used in the training data, if something of that sort demonstration could be done, probably that model will have more yeah, credibility.
No, I think I agree with you. I mean, we cannot, there's no such event in the training, the dating training of the model. Then it's very hard to predict these models. I mean, these to predict the kind of events that haven't happened before, I think they're very difficult. Unless maybe we could look at areas where, certain kind of sea surface temperatures, kind of behavior might increase the probability. There maybe some of the models could help. But I agree with you that. It doesn't mean that they're worse than humans. I mean, for humans, it's also hard to predict these things. Anyway, with that, I would like to thank you, Dr. Arvid. It's a very interesting talk and a good starting point of this session. And we would now like to continue with the panel discussion. So we have 5 panelists, and I'll introduce them one by one, and I'll have some specific questions as well. So we would like to have a discussion about how scientific advancements are currently transforming the early warning systems. So from global forecasting tools to more localized actionable insights, with highlighting, enabling challenges, breakthroughs that connect data to anticipatory action. So that's what we want with early warning systems at the one side, using the knowledge of the biophysical system, but at the same time also interacting with other sciences to ensure that the right actions are taken when we have an early warning. So with that said, I would like to start with introducing Dr. David Farrell. He's at the Caribbean Institute for Meteorology and Hydrology at Barbados. And as probably most of you know, there's a lot of extreme events going on in the Caribbean. So, and it's also often very hard, especially at island scale, to come up with good productions. Dr. Farrell is with the establishment of some new capabilities such as SAND and Dutch Storm Warning Advisory and Systems. He's at the Regional Marine Forecast Support Center. He's playing a pivotal role in advancing science-based services. And what we'd like to ask you, Dr. Farrell, is how are these enhanced forecasting tools, alongside with other pre-existing capabilities, how are these contributing to more effective disaster risk planning and evidence-based decision-making, both at the kind of community and government scale? So how do you use your kind of forecasting systems to get action on the ground? The floor is yours, Dr. David Farrell.
Thank you. Can you hear me okay?
Yeah, I can hear you and I can see you. Perfect.
Okay.
Yeah.
Okay, thank you very much. Thanks for the invitation to speak. For most of you, you would be familiar that I live in Barbados and I live on a SID. And the institute that I work for, that I lead, includes 16 SIDs. And so we provide support to 16 different countries, all small island developing states. Some with coastal lowlands and others with volcanic islands. We were created back in 1967 to provide support to the hydrometeorological services in the region as they were developing in the post-independence period. And since then, we've added quite a bit of capability on top of what we were built to do, which was train meteorological forecasters. We have built certain capabilities in response to what the region wanted. And the region is obviously plagued with tropical storms, one of the most hazardous areas in the world. Tropical storms, volcanic islands, earthquakes, landslides. We have a range of hazards that we need to address. Each of these hazards has an impact on the socioeconomic development of particular islands and for the region on a whole. And so the Institute has been looking mostly at hydrometeorological hazards, climate hazards, marine hazards, and some geological hazards as well. We've been working with regional partners for quite some time. And so we have built skill in areas such as numerical weather prediction, climate prediction systems. We are a regional climate center, and so we built quite a number of climate products and services that support countries in the region. And we also our regional marine forecast support center, the Sun, and Dust Storm Center, and we maintain quite a bit of computational capability, as well as supporting regional observation platforms and climate data systems. And so what we've started to do in the last 15 years or so is start to look at system of systems integration, because we have systems that are occurring. If we look at the climate, for example, we can show that any country can be impacted by multiple climate events in a particular month. And so this poses challenges with regards to forecasting and impacts on economies and impacts on communities and so on. And so we've started to take a more active look at system of systems calculations and how do we start this whole talking about multi-hazard early warning systems with cascading. And so we've started this conversation looking at impacts-based forecasting and looking at areas of impacts-based forecasting and finance-based forecasting. One of the things that we're trying now to move towards, and I'll come back to this later, is this whole idea of how do you move from physical systems to socioeconomic systems and start looking at socioeconomic impacts and finance impacts of financial systems in countries. How do we look at all of this within a complicated trading framework? As most people would know, Caribbean SIDS tend to import almost everything. And so we've got to look at all of this within the climate system that we have and make decisions within the climate system as well as predictions of the climate system, not just in our region, but outside of our region. The source regions, which may be in the Pacific or maybe in Europe or maybe in Asia, we have to look at this as an integrated system. And so we've been spending a lot of time with the various development partners, whether they're in health, whether they are in disaster management, water, energy, tourism, and so on, trying to come up with ways to use weather and climate forecasts to predict impacts to different sectors. And in some cases, you cascade from one sector to another sector. So for example, a heavy rainfall event, which may be good, or a season which may be good for agriculture, may also create problems for health, where one may have vector-borne diseases that thrive in wetter than usual conditions. And so we've been trying to build these systems that allow us to cascade across sectors. And now we're starting to look at how to cascade within economies. As we start to move towards looking at economies, we're starting to move more towards AI and ML strategies to take events that we can see in the climate record and match them against economic shocks that we see in the region and start to try to build out a relationship between climate and weather or geological shocks and how they then translate into the economy. Is there a lag? Is it almost immediate? What is the impact of these different events as they cascade across the different sectors? And so this is a strategy that we're starting to deploy as we move forward. We are working with a range of partners, like I said, from health all the way through disaster management to try to build out these complicated systems and try to build confidence in these systems that they are predicting what they're supposed to predict. And certainly this is the direction that we plan to go, where we integrate the numerical weather prediction tools and climate prediction tools and marine tools, and try to then cascade into AI and machine learning tools that allow us to make more complicated decisions at a faster pace. The biggest challenge that we have, obviously, is data. We have challenges with economic data and getting the economic data at the right frequency. And so many countries will post economic data annually, but certainly we're talking about climate events that are occurring monthly and seasonally. And so how do you bridge that gap and get countries to make data more readily available at the timescales that are required to support their decision making? And so this is the direction that we are going in as we look to mitigate the impacts of weather and climate on the resilience of islands in the Caribbean. Thank you.
All right, thanks a lot for that insight. That was very useful. Then I would like to go to the next panelist, which is Dr. Joanne Robbins, who is from the Met Office. We know the Met Office has made some significant impact on their risk and impact modeling to improve forecastings and warning for all kinds of hydrometeorological hazards. And a question for you is, could you maybe share some insights from a recent project that the Met Office has been implementing, highlighting how it has enhanced the accessibility and the relevance of early warning systems, especially for decision making? I mean, for long-term, Met Offices have worked on improving tools, improving predictions, but very often those have not been landing at the people who actually make the decisions or make the warning. So could you maybe highlight a little bit how the Met Office is trying to improve their impact of their warnings?
Yes, thank you. Hopefully you can hear me okay.
Yes, I can hear you. Yeah, and we can see you.
That's
Okay.
great. Yeah, so thank you very much for the invitation. In answer to your question, I'd like to highlight some work that we've been doing in Southeast Asia. So we have the Weather and Climate Science for Services Partnership, WCSSP, and in this particular project, we're working with several countries, including Vietnam, Indonesia, Malaysia, and the Philippines. In that project, one of the key aims that we're trying to achieve is really to enhance our understanding of tropical meteorology and also how high impact weather events occur in that region. And obviously, to be able to do that, we need to share our forecast information and make it accessible to our partners. So one of the strands of our research is to share high resolution convective permitting ensemble forecasts with our partners so that we can have monthly engagement sessions where we basically talk about what's the model doing, how has it performed for recent cases, what have the impacts been, how did it help influence warning development, if at all, did it help with the narrative, did it help understand the uncertainties with the high impact weather events. And so we have a really informal but quite valuable discussion with our partners around how that information can be used, where it's useful and perhaps where it's less useful. And within that, we've also been starting to do some evaluation work, so leveraging expertise that have come out of the World Meteorological Organization High Weather Project. They developed a sort of assessment process called the warning value chain, and that allows us to assess how information flows through to the generation of a warning and also into decision making at the end. And so as part of this project and this sharing of data, we've been able to then say, well, how good do we feel the observation information is? How good do we feel the weather forecast is? Do we have additional information that talks about the hazards that were critical for this event? How did we reflect on impacts? Did we have impact data? Dr. Farrell was just referring to this challenge around the availability of impact data. In countries that are starting to move to impact-based forecasting, this is a real challenge and is often pulled out through this assessment process as a critical element for future development. Then as we move through that chain, we also look to reflect on things like how was the warning generated? Was the severity right? Was the timing right? Did it reach people? And were decisions ultimately made based on that warning? And were they the sort of anticipated actions that we might have expected? So this is some of the work that we're doing to try and both make data more accessible, but also understand some of the barriers and enablers to accessible data, and simultaneously try and make that data more relevant so that ultimately that value that we're trying to achieve through the warning value chain is achieved and is seen by the stakeholders who ultimately have to make those critical decisions at the end.
Okay, thank you. Thank you, that's very insightful. So after that, we would like to move on to the third panelist, which is Dr. Kenneth, and I'm going to try and pronounce his last name, Sina Chikupo. And we would like to ask him, especially from the perspective of a natural meteorological agency in Africa, what are the key challenges in translating some of the kind of global modeling systems, these outputs, into really kind of local actionable forecast? And you know, maybe you can highlight how the Zambian Met Office is actually addressing that. And maybe you could share some, you know, some experience from a recent example on the El Nino. So El Nino is one of the ways in which we can actually forecast climate quite long-term in advance. 23-24 was a very strong El Nino event, which usually relates to drought in these parts of Africa. So how has the Zambian Met Office dealt with that and trying to actually communicate early warnings? Dr. Kenneth, the floor is yours.
Thank you very much, moderator. Point of correction, I'm not yet a doc, but I hold some master's degree. Yeah, coming to the challenge that as Africa or maybe Zambia face on using the global models is the component of the low resolutions. These global model that we use, they are on low resolution such that it's very difficult to navigate, to produce as a forecaster on duty to produce area specific forecasts. For example, when you use the proof, the WMO, ECM, and UK Met Office and the French Met, those data sources, they are at high resolution. They are basically at global. So when they are at global, the low resolution cause the forecaster to give the forecast at the national level or maybe at the provincial level. Like here in Zambia, we have 10 provinces. So for me to give the forecast using the global models, I would rather just say maybe the northern province. I will not go to specific districts or maybe areas. So that is the challenge. And also there are high uncertainties on these models, both they are at global level. So for you to have the confidence to say what I'm seeing maybe in the wind profile or maybe the precipitation profile, is it going to happen? Because I know that maybe these models are developed in the temperate world and they just maybe try to mimic what is obtaining over maybe southern region of Africa. And also sometimes as a forecaster, I've seen that at many times these models find that they are lagging. They are telling me to say tomorrow confidently that such perturbation will happen in the atmosphere, or maybe that province will have some rain, and yet come the day there's no rain. So sometimes they are ahead, sometimes they are below. So because of that, how do it becomes an issue of verification. So it's very difficult also to verify these models so that maybe you can maybe validate. So because of the developing the temperate world and being used here in Southern Africa and Zambia in particular, these elements of low resolution, lagging, and not able to verify, they bring in uncertainties such that you cannot inform the person maybe at a grid cell or maybe at a district, or in Zambia, Africa, we are divided up to ward level or section level or maybe camp level, especially at agriculture point of view, camp level. You can't inform the farmers in their camp because of these global models that we are using. Because the generation to see the information that most of them are very important, but because of the resolution, they bring a challenge to localize the forecast and then inform the decisions. However, the country Zambia, we are doing some milestone. For example, the government collaborating with other stakeholders and even Ayakira involved, involved. We have installed some automated weather stations in all the 116 districts. I know that we had 72 districts, now there are 116. These 16 districts are covering every corner of the country, and we're able to get data that can inform the people that are outside and able to analyze the forecast to take it to the local situation, local scenario. And also, as a department, we are engaging with research institutions. Currently now we are collaborating with University of Leeds, where we are doing the WISER project. The WISER project has brought in high resolution models that we are using to make a forecast and inform. They have helped us to collaborate with the community, that when we make a forecast, we disseminate to the community through the nowcasting. Then the community, they're able now to translate it to their community members at that level. Because as you know, we follow what the WMO technically those words. So the community is able to translate and interpret to say what they mean is ABCD. So that people are able to do that. Above all, as a department or in the Ministry of Green Economy, we collaborate with other ministries and other institutions that are within the Zambian domain, like Ministry of Agriculture. When we issue the seasonal forecast using these global models, we sit with them to give them the information to say what we are saying is this. So after that, then they go and take it to their camp officers. So the camp officers who are change agents, who work with they live and work with the communities across the country, they will take the message to the people. We also now collaborate with the water people like IWMI. IWMI, when you give them the information, they will take it to the community to advise them, say, the department is forecasting this information, though it has high resolution, but what it means when they're saying above normal, or maybe during the La Nina, or below normal during the El Nino, they will advise people there will be flooding, there will be this. So people, they should avoid certain actions. So that is how we do as a department. And also we are collaborating with the centers of excellence like IRI, Colombia. We collaborate with them to produce to do the sub-season forecast. When you do the 6 months, it's not much. Better you do give the people the weekly, week 1, week 2 to week 3, and the 1 month, something like that. We produce this and share it across the country. And we also hold the television discussions. We send it to the radio. The radio have trained them how to interpolate the forecast, what it means when you say party cloud, what it means when you say the southeastern winds are doing this. They're able to interpret to the people. So what we're doing is to work with the people, because the meteorological language is so difficult for people to get and make an action. So with this collaboration, I think the department, we are moving to do what has been said, impact-based forecasting. Once impact-based forecast and insurance-based forecasting. So we are in collaborating with insurance companies, especially related to livestock and crop farmers, so that when we give this information, they go and take it to the people to say, when there is drought, what happens? And also collaborating with other institutions like UNDP, where we have installed rain gauge, just a rain gauge at a camp level in a village. We install a rain gauge. We train a rain gauge minder. They get the readings. Then before they share with the ZMD, they share among themselves, the community. Then they already train out into what does it mean if it is 20 millimeters. Can somebody do the farming? Can somebody do the fertilizer application? Can somebody do the spraying? Something like that. That is what we are doing at the department, all using these global models, but with the technology that are there, and we are SADC is empowering us with some good computing facilities. We have installed the HPC computers where we are running our own WAF. Though it is at high resolution, low resolution, as I said, it is used to get data getting from GFS. So to downscale from GFS, it requires high internet and good computing facilities. But with that, we are moving to get to the people where they are, so that they get the information, they take early action, they take early warning, and then action. Thank you.
Okay, thanks a lot for that insight. With that, we go to our last panelist, who is from Singapore, works as Thea Turkington. She works at the Center for Climate Research in Singapore, and she's been working on sub-seasonal to seasonal prediction. And we all know that there's quite, still lots of uncertainties around these models, but they can definitely help us with some of the plannings. So how are these seasonal to sub-seasonal forecasts being used and being tailored to really support anticipatory action and planning, and maybe related to extreme rainfall or heat events in this kind of a unique situation of Singapore? Thea, the floor is yours.
Thank you very much, and thanks for having me. Yes, so I think as some of our previous panelists have already sort of highlighted, the real challenge is tying with what is predictable and tying this with the actions you take. And you very well highlighted that as we look into the sub-seasonal, so the next few weeks, and seasonal the next few months, it's not about saying this is going to happen. It's like, oh, there's an increased chance of heat waves, or there's an increased chance of this. So it's nothing's black or white. It's all really about probabilities. So we can look for things to see what's predictable. So even though in Singapore, it's a very, very small country, little red dot, they call it, in Southeast Asia, we can still find that. So for example, all of our past heat waves have occurred during the decay phase of El Nino. El Nino brings warmer temperature, and this coincides with our hot season, and this is when we get heat waves. So this is something that we can already use without the complicated models to help us prepare. Knowing, say, example, last year, there were higher chance of heat waves in our hot season than this year because we're no longer under that El Nino. But as Raghu said in his introductory talk, we also have climate change. So it is, even though we can build these sort of like empirical models, it's also good to look at our dynamical models for seasonal. And we've also been using the sub-seasonal models to look to see how predictable it is for heat waves in the coming weeks as well. So we can get a better idea about within the hot season, when is there an increased chance. You also talked about extreme rainfall. So we actually work in Southeast Asia as well, like Joanne talked about earlier. So we work with a group called the ASEAN Coordinating Center for Humanitarian Assistance on Disaster Management, or much more simply, the AHA Center. And they look at coordinating when there's disasters in the region, provide knowledge, and also support when there are big disasters. So we actually provide them with sub-seasonal outlooks for extreme rainfall. And we know that, of course, this is not going to pick up all the sort of extreme rainfall events, all the events that lead to flooding, especially these small localized events. It's very difficult. Similarly with tropical cyclones. But it does have reasonable skill, and particularly at times of year, it can provide, as our colleagues from the AHA Center have pointed out, guidance to help them in their planning for where they want to monitor in the coming weeks. Now, we're kind of sort of blessed to be in a region where we do have reasonably high skill in Southeast Asia at the sub-seasonal time scale. But our colleagues from the AHA Center have also highlighted that even if you're not necessarily good at extreme, sub-seasonal forecasts can help you after a disaster. And this is probably true for weather forecasts as well. They were giving a case from last year in Myanmar where there had been really bad flooding, and they were looking at the forecast as well as longer-term sub-seasonal forecasts for helping guide them when should they be moving people back into the village, given that there was extensive flooding, and will they have to come out again as well. Finally, I just want to highlight also through our work in the region, the actions that you take are just not necessarily the same actions you would take with the weather forecasts, but some things can take a long time. So we had colleagues from SCAP, which is another group working globally as well, and they were highlighting how, I think one of our earlier speakers, David, was talking about forecast-based financing. And sometimes this takes a little while to get the money to come through. So perhaps using sub-seasonal forecasts where it is skill at highlighting certain extreme events, you could use it to start the process. And then afterwards, use the more detailed weather forecast to actually trigger that final action. So yeah, the challenge really, to sum up, is looking about what's predictable and then talking with the people that could potentially use it and identifying with them what sort of thresholds, what sort of variables you should be looking to help them take action.
Okay, thank you very much. And I think you started off very nicely. It's about looking at what is predictable and how can you, based on what is predictable, really lead to certain actions. And you're very right that at seasonal scale, we take different actions than we take from a kind of maybe early warning system from an extreme event based on the weather forecast. And of course, yes, you're lucky to be in an area where there's high skill in terms of seasonal forecast. We've tried things in Europe, but it's very difficult and it's very limited skill. So yeah, thanks a lot for that. I think we have a few minutes left from some for questions for the panelists. So I'm not sure if there's anybody from the room who wants to raise his hand and ask questions live. You can also still put them in the Q&A. There's already been a few questions, and then some of the panelists have already answered those. So thanks a lot for that. If nobody, maybe I do. I think there was a very interesting question which was already answered by Joanne, but maybe some of the other panelists want to give a go as well. So here she's saying, like, the focus is on predicting, but how, if we know that a prediction is right or there's a high chance of an extreme event happening, how do we make sure that people actually listening to the warnings, and how do we encourage them to really take action on their own based on the predictions, and maybe, I don't know if there's examples from behavioral science or basically based on your work. So I'm not sure who from the panel would like to answer that. How do we stimulate people to really take action based on the warning? Anybody?
Maybe
Yeah,
I can just add something. Yeah. Unfortunately, I can't give a nice example from behavioral science, but I just want to emphasize the importance of trust. Building a good relationship, being honest about the quality of your forecast, assessing the forecast. I think this helps when you have trust, but it's not easy to build trust. It can be easy to break trust as well. But yeah, I think this is really key.
David, go ahead.
Thank you. We've spent a lot of time on this particular problem. In fact, we have brought in social scientists within the Institute to help us build relationships with different socioeconomic sectors. How do we get the downstream users of information to utilize the information? How do we move the information really from a science context to really a sector context where the sector persons or people in communities actually understand the information and can action the information? And so we've spent quite a bit of time trying to address this particular problem, because we recognize that it is a problem, and it is becoming a bigger problem these days with misinformation and disinformation, certainly via the internet. And so we've spent quite a bit of time working with downstream users to really take the science information and put it into a context that people can more easily understand.
Foucault, we have been from a participant, Emmanuel.
Yeah.
You go ahead.
Yeah, thank you very much for your presentations. Quite insightful. I have heard a lot about the turbulence within the climate systems from India to Africa, somewhere Tanzania, right? And then even Indonesia. Now there is an emerging interesting research that keeps on coming on our decks, and that is on the value of integrating this model output with indigenous kind of knowledge on forecasting the rainfall and other climate systems, right? Now, my question is, I have not seen any of you reflected on that element in your presentation. Research has shown that some of these knowledge system and data sets from local people can improve upon the accuracy and then also acceptability of these forecasts. In your opinion, and or perhaps from your experiences across board, what do you see, and what do you see as a value of this in your work or in us improving the predictions and making the unpredictable predictable.
Anybody want to give it a go?
I can take that.
Yeah, go ahead. Go ahead.
Yeah, the local traditional knowledge is very crucial and it's important. And the forecasters, the actual final forecaster and the warning issuing agencies, the actual people who are working, they generally and always, as a thumb rule, they use the traditional knowledge, the local climatology, local agricultural practices, historical changes, all those things they definitely use in forecasting. I don't think they have given up anywhere else, maybe in India, even in other countries. The final forecaster always use the local things. They don't completely trust the numerical models. They use them for guidance and as a advance early information availability, but final warnings are always based on this thing. And also the communication is important, how to make it more relevant for a particular situation, depending on a city or a town, and what kind of an information is critical for them. I think it's packaging also helps, and that definitely requires the local knowledge and the traditional knowledge, and also the traditional practices of agriculture or whatever, any activity over certain regions. Yeah, I think it is very much used by the forecasters.
Okay, thank you. David, do you also want to respond to that? Or not? I think he. Kirai, how much time do we have left? Do we
We
need
are
to?
already past 1 minute. Maybe we
Okay.
cannot take more questions, but request the participants to share your questions. We'll be happy to respond to that. Over to you, Fulko, to summarize, and then I would be happy to.
Okay. Thanks a lot, and I'm really encouraged by what I've been hearing today, because I think when we were started to work with Met officers 20 years ago, I think a lot of it was very top down, kind of giving information, data, models, outputs, and then basically not thinking about actually what actions you trigger. And I think today we're a lot further than that. We think about, how can we use and improve forecasts, but also how can we make sure that those forecasts are actually used by the people and landed to people, and how can we look at early warning systems which both, give information from the weather and the climate science, but also, land, I think as one of the speakers was saying, in the sectors. And different sectors need different information. I think also, different kind of warnings ask for different responses. At seasonal timescale is a different response than at the medium timescale. And I really like the example of also using the forecast after a disaster, like how actually do you reach people? Because sometimes it makes a big difference if you have a flood and then it's dry for a month, or if you have a flood and it continues to rain. So I think also those are new uses of the kind of information that help people to recover from disasters. So thanks. I would like to thank all the panelists and our speaker for a very interesting interaction and very interesting discussions. And with that, I would like to hand over to Girai, who tell us about the upcoming events.
Thank you, Fulko, for nicely moderating and also beginning with Dr. Raghavendra and all the panelists for providing this interesting insights. Of course, we need an early warning to even close our session 4 minutes before, and a very interesting moderation you have done. Thanks for that. And let me just share my screen to all the participants who are joining us. So the next webinar session will be on the heat wave. Just Tia was talking about the heat wave is a major problem now. And we have global experts joining from WHO, WMO, and John Hopkins and Harvard University, and as well as the local level municipality, how they are tackling the SOPs that would go from the climate forecast agencies to early action planning that the agencies would look at. So do join us. It will be an exciting session. So we would highlight the upcoming session that was happening on 6th May. Soon there will be a Zoom registration will be shared in our website for everyone to join and take part in this expert discussion. Thank you with that, and we would look forward to future sessions as well. Thank you again for joining. Thank you. Over to